Hey y'all, here we go. Implicit differentiation. Examples of explicitly defined functions have y on one side and everything else on the other. Examples of implicitly defined functions have x and y all mixed up, and usually it's difficult to solve for y. Okay, so we're going to start with I guess it's not number one, but y cubed, I'm sorry, my cat is playing with her toy right now, if you can hear that. Given y cubed plus y squared minus x squared equals -4, we are going to differentiate with respect to t. Since you must apply the chain rule, each derivative will have d blank over dt as part of the derivative. And what we mean by that is we will have the derivative of the variable with respect to t. So when we come down to y cubed plus y squared minus x squared, we need to bring down the power, subtract 1 from the power, and remember that we're differentiating y with respect to t. So there are some new pieces here, and I've already alluded to some of them. We are differentiating with respect to t, so when you get to dx over dt, you no longer have something that goes away. So we're going to talk about that not at step C. So you actually have to write out the derivative of x with respect to t. And you've never had to do that before. So moving along, we're going to differentiate with respect to w. Since you must apply the chain rule, each derivative will have d blank over dw as part of the derivative, or we're taking the derivative with respect to w. And it looks almost identical, except instead of dt on the bottom, we have dw. Now we're going to move on to C at the next page. So when we get to C, we are going to differentiate with respect to x. And that creates something that we're familiar with, but also a unique phenomenon occurs. So if you look at this one, you see that we have dx over dx. We've never written that before. Well, there's a logical explanation for that. Dx over dx is just something divided by itself, so it actually simplifies to 1, so we actually don't need to write it. And this right here is what we're used to seeing. We rarely write this step. In fact, it's highly unusual to write that step. Now, we are going to solve for dy over dx by getting dy over dx on one side and everything else on the other. So just like Algebra 1, we add what we can to one side. Now we're going to factor out the variable that we want to solve for, and the variable that we want to solve for is dy over dx. Once we factor that out, we're going to divide both sides by that bit right there. That didn't underline well, did it? And we have solved for dy over dx. It still looks pretty goofy, but I promise we will find uses for it. Next up, we're going to find our derivative dy dx in some unique equations. In this first one, you need to remember product rule, and I'm going to write out every single step here to make this very, very clear. The derivative of the first times the regular of the second plus the regular of the first times the derivative of the second. And this bit right here is just power rule. and the derivative of the constant is 0. Now, if you remember from the previous bit, this dx over dx, that's just 1, because something divided by itself is just 1. So I'm going to go ahead and simplify. And then we're going to go ahead and get everything but the dy dx. I'm sorry, we're going to get dy dx on one side and everything else on the other. I kind of started to say it backwards. Just some good old-fashioned factoring, and then we're going to divide both sides by x minus 2y, and we'll have our dy over dx. Okay, we've solved for dy dx, and I want to point something out very quickly that I may not have made clear to all of you. If you look in that very first step where I highlighted the dx over dx, we usually skip that step. That step is not necessary. That's just me over-explaining. On this next step, we have product rule again. And we're going to use product rule, and we need to remember our derivative of cosine and our derivative of sine. Okay, I accidentally ran out of room, so this actually moved to this side. The derivative of a constant is 0. Then the derivative of cosine is negative sine. Bring down the regular of the second, which would be sine y. Then cosine x, that's just the normal of the first. Then the derivative of sine y would be cosine y dy dx. Why didn't I have a dy dx in the first one? Because we were actually taking the derivative of, the cosine of x. And the cosine of, the derivative of cosine is x. Whoa, I can't talk. The derivative of the cosine of x would be negative sine x dx over dx. And remember, dx over dx cancels. We rarely write that. We don't need that step. That's what I was just talking about over here. We don't need that step right there with the dx over dx. We hardly ever write that. So, moving right along, we go ahead and solve for dy dx by getting dy dx on one side and everything else on the other. Once we have it in this form, we see that it is simply tangent x, tangent y, and we are done. Okay, there's some directions at the bottom here about using a TI-89. If anybody has a TI-89, you might find that useful. However, a TI-89, the AP Calculus exam is built in such a way that a TI-89 doesn't help you at all, and if you're taking calculus in college, they don't allow you to use a calculator. So this one asks for the second derivative, and the second derivative has odd notation. When I have time, I will go over how this notation comes to be. It is not very interesting, I'll be totally honest. Just know that the note where those 2's are, it's d squared y over dx squared, which looks like nonsense. There is a reasonable explanation. And again, if I have time, I will explain that to you. Okay, so we take the derivative and we remember product rule for that x plus y, the regular of the first plus the derivative of the second, plus the derivative of the first times the regular of the second. That's what happened right here. Okay. We are going to solve for dy dx. And once we're done with that, that's when the magic begins. I took those first 2 terms and I factored out the dy dx. I moved the y to the other side. And now I'm going to solve for dy dx. Now we're going to take the second derivative, which involves going low, d high, minus high, d low. So we've taken the derivative. And this is where I see a lot of mistakes – when I am grading for College Board in Kansas City. I see that everybody, or I would say about 50% of the students in BC who take the AP exam forget to plug in the value of dy dx. You know what dy dx is. It is right over here. So now you can use it. And by the way, fun fact, AP exams, the scoring of AP exams is determined by colleges that are members of the College Board, and that does include Harvard, even though Harvard does not accept AP exam scores. They wait, if a student in college is in calculus and they get an A in college calculus, and they also take this AP exam, which they do, they take some sort of, I don't know if they're part of a study, I don't know how it works. Maybe they just take it for their professor as their final exam. And let's say they're getting an A in their college calculus class. Then it is determined and averaged out over the country that this particular cutoff score means that a student will get an A, and then you students will get a 5. So a 5 on the AP calculus exam is equivalent to an A in college calculus. If you want me to explain that more in class, I will. Now, if you look at this carefully, this term will cancel with this term. And when you simplify, you see that these y's cancel, and you are left with y squared over 2y plus x cubed. And I'm sure y'all noticed I missed a sign in here. This right here was a negative dy over dx. So a negative dy over dx would have turned this positive, which also turns this positive. And y'all, I randomly dropped a 2. There should be a 2 right here. I just did some very creative math. Sorry about that. Fixing it now. We get y minus 2y squared over 2y plus x plus y. Okay, so I had to rewrite this because I do not think well when I'm trying to squish things on a page. So now we have 2y minus 2y squared over 2y plus x. We need to find a common denominator in that big numerator. So I'm going to work on that real quick. Okay, so I found the common denominator. Now I'm going to write it over the common denominator, and I'm going to actually, I don't like using this kind of language, but I'm going to FOIL this out real quick while I do that. Or distribute it, that's better language. Once you've done that, you can combine your denominators and your like terms in the numerator. Now, if you have a really good memory, or you actually happen to fit this on the same sheet, this should look somewhat familiar. If you factor out a 2, you actually have your original expression. And in your original expression, you knew what y squared plus 2xy was. So go back to your original expression, and you see that it's 25. So you replace that y squared plus, I wrote 2. Y'all, I don't even know what to do with myself. Okay, so y squared plus xy is 25. So you replace it, and you get 2 times 25 on top, and that's just 50. And voila, there's your answer. Okay, we'll take the derivative using implicit differentiation. Once we've done the initial differentiation, then we are going to factor out a dy dx and solve for dy dx. And this process should be getting clearer to you. So I'm going to skip a step here. Easy peasy, pumpkin squeezy. We're going to find the equation of the tangent line to the curve at the point 1, -3. So we find the slope by replacing x with 1 and y with -3. We also need to do that. We will eventually need to do that in... We already know what our point is. All we need to do is find our slope. I lie. I don't know why I started that sentence. There we go. Plug in x and y into our slope, and we'll have our slope. Then we're going to use point-slope form. So this particular piece should be fairly easy for you. Suddenly you find in calculus, it wasn't until I got to calculus that I understood the usefulness of point-slope form. In point-slope form, just for those of you who don't remember it, just in case, because some teachers hardly touch on it at all, this is what point-slope form looks like. And it looks like this crazy, kooky thing, but all of a sudden you get to calculus, and this is so much faster than putting it in slope-intercept or y equals mx plus b form. Slope-intercept and y equals mx plus b form are the same thing. Okay, so you've got it in point-slope form. You are done. You don't need to do anything more for b. Moving on to c. In c, it asks you for the coordinates of the points on the curve where the tangent to the curve is vertical. So we're looking for the places where the slope does not exist, and that would be where the denominator in dy dx is undefined. And dy dx is undefined, again, when the denominator is 0, because you cannot divide by 0. So we are going to set our denominator 3y plus 5 times y minus 1 equal to 0. So we have found the y values when the slope is undefined. Now we need to find the x values. So we'll start by replacing y with 1. And when we solve for x, we get plus or minus 1. Now we're going to do the same thing for -5/3. So I'm going to go ahead and solve for x squared, then I'm going to square root both sides. Once I've done that, I'm going to replace y with its value, which is -5/3. Then we simplify without using a calculator. Tips and tricks. You could simplify this further. If I were you and I was taking the AP exam or even my final exam in calculus, I would stop there. That right there is a number. There is absolutely no need to go any further unless it is a multiple choice question. If it is a free response question, even in college, that right there is a number, unless you have some professor who wants you to simplify, and they will be very clear if they want you to simplify. So your answers are as follows. This is how you write your answers, is what I'm trying to say. And now for a special treat. This is me around 1992 in the village of Covey when I was serving as a Peace Corps volunteer. I am wearing shorts in this picture. I just had a huge t-shirt on. Anyway, I'm in Covey, and I wish I had the rest of the photos. They are actually in my classroom. I'm at the bottom of a waterfall. It is so beautiful. This This was one of the most gorgeous places I ever visited when I was serving in Peace Corps. Doo-doo-doo. Then here is the Atlantic Ocean from the city of Ouida in the country of Benin. I lived there for 3 years of my life, and the ocean is approximately 1 mile from where I lived. As you can see, it is not a sandy beach. This is Ouida, and in the middle of the picture, you see this guy carrying a grass mat on the back of his little moped, and that little moped ordinarily carries 1 to 2 people behind the driver. Very common. Did it a lot. Sometimes I'd pile on with 2 of my friends and the driver, and we would zip around town. Yep, that was the life. I don't even know how we all balanced in there. I have so many funny stories from my experiences serving in Benin. This is what I consider a normal road in Benin. It's all dirt. Everybody's walking with stuff on their heads. It is a little washboardy. My friend Mark lived very close to me when we served in Benin. He only lived about 30 miles away, and we would ride our bikes back and forth between our villages to talk to each other all the time because we didn't have phones. So we got really accustomed to riding on these dirt roads with our bicycles. We had little trek bicycles that we would ride. We would see each other almost every weekend. This right here is if you know French, which I do, it's talking about hairdos in the words. And this is basically a beauty parlor. Why the door is so high up, I don't know. Why the door handle is so much higher, I don't know. But this is in Mark's village of Comé. These are very recent photos, by the way. This right here is the what once was the Portuguese fort in the city of Ouida. It is now a museum for slavery because Ouida was once the largest slave trade port in all of West Africa, actually in all of Africa, and it is also considered the world's capital of voodoo. So I learned a lot while I was there about the other half of the story about the slave trade and how different voodoo is in the country of its origins than it is in, say, for example, New Orleans. But they have remodeled this significantly since I was there because tourism has become quite the thing over there. Next up, we have the Rue des Esclaves, translated literally Road of the Slaves. This statue is brand spanking new. There were no identifying markers when I lived there. Then here we have a market. And if you look at the market, it looks like there are watermelons in the picture. And, well, you see a lot of tomatoes. Those watermelons are actually coconuts. I had to really zoom in on it to figure it out. One of my favorite things, and I really want these. See these stinkers right there? Those are sleeping mats. And I want one, and I cannot find one. Amazon is doing me no good. Women make those sleeping mats. I suppose men do too. I never really thought about that. And these beautiful baskets, all very, very, very handmade. And I don't know why the only thing they're selling here in this market is tomatoes. There are lots and lots of fish in Ouida. I ate fish every single day. And Ouida is one of the few cities in Ouida that has a market every single day. And that's only because it's a relatively large city. about 30,000 people. So it's not like a tiny little village in the middle of nowhere. I can answer any questions you want about this, including how women wear buckets on their heads. It's a lot easier than you think. This is called the Tree of No Return. They have sculpted into the trunk, since it was actually used as the Tree of No Return. When it was used as the Tree of No Return, the tribes that are close to the coast would capture their enemies, sell them into slavery, and make them walk around this tree some crazy number of times, like 50 times, before they would lead them to the boats where they would be shipped overseas. And then I took it twice because, I don't know, that's yuck. Anyway, I don't like that I thought about that twice. Then there's my friend Mark. And if you saw a picture of him, which is in my classroom, when he was actually in Peace Corps, he has changed quite a bit. I have too, so that's okay. Okay, y'all have a good one. Take care. Bye-bye.